This is Cosmographia, the Randall Carlson podcast. Welcome back, ladies and gentlemen, to Cosmographia, the Randall Carlson podcast. I am Russ, and I'm joined here by the entire Cosmographia team. And I think we're going to continue this week on Randall's evidence against ice dams, at least in the context of the Younger Dryas and the Missoula floods. Right, Randall? Is that where we're going this week?
Well, yeah, because let's be clear, I'm not against ice dams. They have their place.
Totally against them. Right. Down with ice dams.
No, Russ. Russ, like I said, ice dams have their place. We have to look at it in context, and that's what I'm planning to do a little bit, because there's been a lot of research on ice dams, outburst floods, Jokulaups, if you want to use the Icelandic term. So we need to look at that a little bit, because I don't think we are going to be in a position to formulate a realistic model for the outburst floods that created the Channeled Scablands without kind of looking at modern analogs. And the modern analogs would be outburst floods that have been particularly prevalent the last couple of hundred years. And the reason for that is because of the massive glacier expansion that took place over the course of the Little Ice Age. So, we're in a position where we were able to see a smaller version, a micro-scale version, if you will, of what happened at the end of the last Great Ice Age when we look at the ending of the Little Ice Age. Now, just to recapitulate the general idea here, the Little Ice Age was a multi-phased climatic event that started in the late 12, early 1300s, and essentially concluded between the early and mid 1800s or 19th century. Now, there were a couple of phases within that, because it wasn't an unbroken period of cold, but it came on the heels of the medieval warm period, which, and again, it's not uniform over the whole planet. In some places it comes on sooner, other places later. In some places the effects of the changes are more pronounced, in other places less pronounced. So we see that pattern going both with the onset and termination of the medieval warm period and the onset of the Little Ice Age. Now, however, the medieval warm period generally lasted from sometime between 900 AD and 1000 AD until the end of the 1200s and the early 1300s. And once it ended pretty quick, within a couple of decades. And the Little Ice Age came on. It wasn't a smooth event. It kind of came on in a series of fits and starts over a period of 2 to 3 decades. So the medieval warm period was a period of prosperity. It was a period of abundant agricultural harvests, of plenty to eat. We've talked about that, but it never hurts to reiterate some of these ideas, because they have important relevance for what's going on right now and the discussion about climate change that's going on right now. And what we see during the medieval warm period was preceded by the so-called Dark Ages, which was also a period of global cooling and cold that lasted between 3 and 4 centuries. And it began in the early 500s. The decade from 536 AD to 546 AD is considered to be one of perhaps the coldest decade of the last 2,000 years. And one of the interesting things about that we're going to explore in future podcasts is the connection between that particular time and some of the Grail Mythos, because the Grail stories are actually set right in that interval that marks the onset of the Dark Ages. How we know that is from the stories that link King Arthur's death at the Battle of Camelon, that is generally dated to around 540 to 542 AD, which pretty much defines the epoch in which all of the Grail stories unfolded, with the formation of the Knights of the Round Table, Camelot, the quest for the Grail. And of course, all of that was predicated upon the idea that the Grail was the antidote to the pestilence and the chaos that had come over the kingdom, the land, and had turned the previously fertile and fecund land into a wasteland. And simultaneous with the transformation of the land into the wasteland, the king fell ill, whether it was King Arthur or the Fisher King or any of the others that are named in the Grail stories. And they do all vary. It's generally the same idea that the king was ailing and the land was ailing, and the Grail was the antidote that could heal both the king and the land. And there's some really profound ideas in there. But what's interesting is that the whole Grail stories are placed right within that epoch where there was essentially the end of the Roman warm period and the beginning of the Dark Ages cold period. So then you had the Dark Ages cold period that lasted for 300 to 400 years. The 542 AD, which was right within that decade of extreme cold, came the first major year of widespread agricultural failure was 536. In fact, that year was a year now, it looks like, of literal darkness. There was several years in there that were probably the result of literal darkness. And that would have been brought on by one of two possibilities: volcanoes or cosmic impacts, or perhaps both. And in fact, what's interesting, and again, we'll explore this later on, is there's some evidence suggesting that within a decade or two, there was actually 2 impacts and several major volcanic eruptions. Whatever the mix turns out to be, in any case, we have the deterioration of the global environment between starting like the mid-530s. By 542, after a period of malnourishment, because people weren't getting enough to eat, when people become malnourished, they become susceptible to infectious diseases. So 542, you had what's called the Justinian Plague. And the Justinian Plague annihilated at least 3/4 the population of Europe. We don't know. I haven't seen the studies in other places around the world, but at least as far as European history goes, there was a major curtain that came down on European history around that 542, subsequently followed by the so-called 3 or 4 centuries of the so-called Dark Ages.
Where were the impacts possibly?
Well, there was one perhaps that looks, and these are tentative because they haven't been proven yet, because they both appear to be oceanic impacts, one off the coast of Norway and one off the coast of New Zealand, are the two that I know of. So,
wow.
Yeah. Wouldn't that be something if
that was that recent? That should change a lot of probabilities and timelines. Right? Absolutely.
Well, we're going to circle back to the evidence, because we haven't really gone down into the nitty-gritty of impact events in the Holocene.
Okay.
But we certainly need to. And that's high on the list of things that we need to be looking at. Because even if we talk about a Younger Dryas impact, 13 or 14,000 years ago, in that range, we can still try to comfort ourselves by saying that was a one-off event. Right. And actually an impact event of that magnitude is unlikely to happen again. However, you could have an impact event that's 1/10 or even 1/100th the magnitude of what the Younger Dryas impact appears to be, the scale of that event appears to now be. And it would be major disruption to global civilization. Major disruption. So then you had the medieval warm period, During the medieval warm period, you had abundant crops. The growing season was, a good month longer. You had, on your elevation, your uplands, you were up to 500-600 feet higher in the uplands where you could grow crops, right? And so vast areas, for example, of Scotland, which were not farmable during the Dark Ages, were now farmable during the medieval warm period. Any mountain area, mountain valleys that oftentimes were within that transition zone now became viable places to grow crops. So you had a huge expansion of arable land with the onset of the warmth.
And has it gone back down since then? Like, is it a couple hundred?
Oh yeah, it definitely went back down during the Little Ice Age.
Yeah. Is it back up basically to where it was before, or
no?
Now? No,
it's not.
Yeah.
It is not.
It. Yeah.
And we're going to get into that. Okay. We're going to be talking about, we're going to devote a series on climate and environmental change throughout the Holocene.
All right.
And during there, we're going to look at a lot of stuff. We're going to look at temperature changes. We're going to look at what the sea has been doing. We're going to look at volcanoes. We're going to look at potential impacts. There's a lot to, there's a lot to unpack to figure out what's going on in the Holocene, because basically the whole of our modern history is within the Holocene. And it's going to be a very interesting exercise now to begin to look at history and the vagaries of history within the context of natural global change as it's unfolded throughout the Holocene. And as we've talked about before, the beginning of the Holocene, coincides with basically all of the rudiments that later evolved into civilization, starting with agriculture and farming between 8,000 and 11,000 years ago, right? The domestication of animals, the dispersion of languages, the first urban complexes. All of these things begin to show up between, say, like 8,000 and 10,000 years ago, right? So the thing I've said before, and I'll say it again and repeat it, I think we need to be considering that what we're seeing there could possibly be not the beginnings of civilization, but a rebooting. It certainly was a rebooting of the global biosphere, no question about that. Then the question becomes, what was going on with humans during that time, with human society? And which brings us back to that idea of what kind of civilization may have existed back in the Ice Age. And of course, there we have to be careful, because a lot of times people will just say, advanced civilization, without being specific about, well, what do you mean by advanced? And for those folks that have gone back and revisited our early first series of podcasts on Atlantis, one of the things that I'm saying there is, it's not such a stretch to assume as a working hypothesis that there may have been a maritime capable civilization of some sort during the Ice Age. Given what we now know, that is not at all implausible, other than the fact that whatever your bias happens to be. But I think we have to be open to the possibility now, and we haven't explored it yet, but we certainly will. The evidence that points directly to there being another order of human activity, during the latter part of the Pleistocene than has been imagined, in the models of conventional academia for the last century. We have to, I think, admit that the evidence exists that there was a lot more going on. But what form it took, and specifically how it evolved and how it disappeared, are open questions. But I think once you begin to appreciate the extraordinary level of climatic and environmental change that this planet has been through during the last 10, 12, 15,000, 20,000 years, it becomes obvious why, you don't see the overt evidence of human occupation on some scale that we would think of as civilization. Because, look, if the Younger Dryas scale event happened now, and then the sequence of events, because see, again, we're not looking at a single event when we look at that transition out of the Ice Age. We're looking at a cluster of events, right? And maybe some of them were a couple of orders of magnitude greater than others. But when you're looking like we're going to be talking about here now, the Missoula floods were 3 orders of magnitude larger than any of the biggest modern floods that have been considered catastrophic. Well, if you consider, in the last episode, we looked at, I believe it was Hubbard Glacier, and an example of a Yokalaups, and one of the largest discharges documented in the last couple of centuries. And I should go back to say that what happened is, with the onset of the Little Ice Age, glaciers worldwide began to grow. Got to keep that in mind. So that by the 15 or 1600s, 1700s, glaciers have now gotten the largest that they've been throughout the entire Holocene, right? By the 1800s, early 1800s, we're looking at glacier mass balance shifting to the positive side to any greater extent than it has been since the end of the last ice age, right? So we go back 10 or 11,000 years, let's say 10,000 years, because earlier than 10,000 years, we're going to still have a considerable mass of stagnant dead ice left over from the Great Ice Age that's melting away over a period of a millennium or two. But if we assume, if we go back 10,000 years, we're not going to find at any point on this planet the glaciers being as extensive as they were during the last, say, 200 to 300, 400 years ago. So this is very important to keep this context in mind when we talk about, number one, when we talk about the present day circumstances of glaciers, the shrinking glaciers, which they've been doing literally for 150 years, literally for twice as long as we have been putting significant amounts of carbon dioxide in the air that could potentially cause global warming. For twice that long, the glaciers have been receding from their Little Ice Age expansion. But the thing is, with that Little Ice Age expansion, it was by witnessing what the glaciers did on that scale that allowed the early geologists, Louis Agassiz being the principal one, but others, to go out there and see, picture now, glaciers have grown, right? During this period, like from the 17 to 1800s, glaciers have grown and they've swallowed up farms, they've swallowed up villages in valleys where people have been living for generations, literally for generations. And, we'll be getting into this because there's some very interesting stories from this time where, the whole village would come out and the village priest would be doing prayers and asking forgiveness for the sins of the village to try to entreat God to stop the advance of this massive wall of ice that's moving down on them. So these people weren't, they were looking at the downside of glacier expansion, not glacier recession. So now, but at the same time, you've got natural philosophers, because at this time, geology, the geological profession didn't exist. They're going out there, they're seeing the glaciers expand. They're seeing the moving, dynamic, living ice delivering moraine to the snout of the glacier. They're able to see the formation, directly observe the formation of medial moraines, of lateral moraines, of terminal moraines. Then once the warming began and the ice began to recede back, they could see that it would recede back, it would pause, and it would pause a few years, a decade or two, and during that time it would build a recessional moraine. So they were able to see over a period of 100 to 200 years, they were able to firsthand witness all of this. Well, what this did was it basically gave them the eyes to see the evidence for the Great Ice Age. See, that's the important part of this. But in any case, because of the fact that you had, for example, tributary glaciers coming into a main trunk valley, there's a large glacier in the trunk valley, the warming begins, and the tributary glaciers, which are smaller, they will be the first to melt. So now you have glacial meltwater ponded against the main valley glacier. And the valley glacier is shrinking. As it's shrinking, the lakes are increasing in size. So what has happened is, if you look at the studies of glacial outburst floods, they were very prominent and destructive in the late 1800s and early 1900s. and they're declining. Now, this doesn't count like Vatnajökull, which is the glacier floods from the volcanoes under the ice sheet in Iceland, because that's a different mechanism. That's geothermal energy coming up from beneath the glacier, melting the glacier and creating a reservoir of meltwater that then bursts out, right? But when you see the general warming of the climate and you see all of these lakes forming, they're held in by ice dams, and then those ice dams give way. But as the ice is shrinking back, the size of the lakes ponding against that ice is shrinking as well. And eventually, if you've got a trunk valley filling a glacier, once it's shrunk back, right, and exposed the mouths of those tributary valleys, there's not going to be any lakes forming there anymore. Can you picture that? Because the ice, the main trunk glacier is down here. Here come the tributaries back here. They're melting away. They form lakes. And then sometimes when the lakes get deep enough, they force their way through the ice, and then they burst out of the snout of the main glacier in a catastrophic flood. But as the main glacier recedes back and eventually opens up those valley mouths, boom, no more proglacial lakes, no more outburst floods. And what we see is that the magnitude of the floods, outburst floods, throughout the 20th century has been diminishing, decreasing. So, yeah, they were pretty prolific when the first really serious melting of the Little Ice Age glaciers began. But they're diminishing in size. They also are occurring quicker. In other words, when the glaciers were bigger, you might have 10 years between outbursts. As all of this is getting, is this whole system is shrinking back in scale. Now you might have outbursts every 4 or 5 years, then every 2 years, and then every year. And each time they're getting smaller, right? Because the magnitude, the amount of water that's pooling, the main glacier that's forming the dam has shrunk back. So now the volume of water that's able to impound is smaller, see? So this has been the trend of the last 100 or so years. But there's now a lot of data and so forth from the studies of this unique time, because it's basically over until the climate cools significantly again. The glaciers grow, but we're looking at, even if that happened now, it's going to take a couple of 100 years for the glaciers to grow back to their Little Ice Age maximum, presumably, unless we're overlooking some process that can rapidly accelerate the accumulation of glacial ice. But if we look in terms of how long it took those glaciers to expand from their recessed medieval warm period, when farms and villages were being formed in the valleys in the Alps and the Jura Mountains and in Europe and up in Scotland and things like that, between that time and the time when they were finally being overrun, 1 to 2 to 3 centuries, depending on regional and local conditions. So, Kyle, you had something you wanted to comment?
Well, I think it would be more terrifying to see the winters getting longer and more severe and crops failing and glaciers taking over towns than a couple of inches of sea level rise.
Well, I would have to agree with you. Now, as
and
to
longer,
matters,
longer growing periods, and I don't know.
Well, yeah, no.
Yeah.
All you have to do is look at history. During the medieval warm period, you had crop surpluses, and on every statistic, from population growth. So during the Dark Ages, population either stabilized and didn't shrink, or it shrunk. Not even including the devastating effects of a plague event, right? Because clearly at the beginning of the Dark Ages, there was a major plague that wiped out, huge percentage of the European population. So now you come to the medieval warm period, and you had Vikings growing crops on the west coast of Greenland where it's been permafrost, right? They were there for 400 years? That was the medieval warm period. You had a wine industry in England 400 miles further north than it is now able to cultivate wine, except for now that's been overcome because of genetically engineered crops.
Yeah.
But excluding that, yeah. So, and then with the onset of the Little Ice Age cold, all that came, the whole wine industry in England collapsed because they couldn't grow wine grapes anymore. But yeah, I mean,
the other thing is that it's a fact that it is going to come back. Like the ice is going to come back at some point, which is just a matter of time. It's like,
well, you figure over the last 2.6 million years, it's probably come back. We've gone through maybe as many as 12 or up to 2 or 3 dozen glacial interglacial cycles. And the longest period of interglacial cycle doesn't appear to be any longer than the Holocene.
right.
And most of them, even the Eemian, which was considered to be the analog for the Holocene, was considered about the same length of time, which it was, except that the Eemian had several major interruptions in it that were pretty spastic. The planet was spazzing a couple of times through the Eemian, which, which if that happened now, we haven't had any climatic upheavals on that scale throughout the Holocene. The closest maybe was that 8,200 to 8,400 year ago cold event, which still doesn't have an explanation. But that would suck if something like that, 8,200 to 8,300 years ago, happened right in the middle of the hypsothermal that lasted, from like 9.5 to 10,000 years ago down to about 6.5. The climatic optimum that it's been called, which was a period of greater warmth than now, no question, and probably higher sea levels as well.
Every time we have one of these discussions of the ice ages receding and advancing, I'm reminded of the graph that you've shown in the past. For all intents and purposes, you look at this graph, and it looks almost like a heartbeat.
Mm-hmm, mm-hmm.
Okay, and it's regular. I don't know if you can access that and pull it up right quick to show the one I mean, but it shows the mean temperature. I guess it's the Greenland temperatures, but it's regular. These things come, and it's a very distinct pattern. And what strikes me is we're at the high end.
Mm-hmm.
This thing varies, and throughout history it goes low, but we're at the high end. And historically, if you look at that graph, we're due for a sudden drop. I don't know if you could access that graph quickly or not, but that's always astounds me when I look at that.
Yeah, I agree, Mike. I know what you're talking about, and the same thing struck me, that we seem to be at a peak.
I think you're talking about this graph.
Something similar. I think it's a larger. I think that's that's the tail end of the graph that I see. The one I'm talking about is a longer time scale.
Well, this is 400,000 years.
Is it?
400,000 years. And what you see here is, let's see, I think, there we go. This is our modern warmth right here.
Right. That's it. Okay. This is one of the graphs that I'm talking about. It's not the graph that I had in mind, but it's one of those. It looks like a heartbeat.
Yep. I think I know what you're talking about too, Mike. That's cool. This is a good illustration of it.
I think, Mike, you might be talking about.
I think that one's from the early 70s too.
Yeah, you might be talking.
How did they measure that? It said it was
90s.
temperatures in the surface temperature of the ocean. Is that
the Caribbean. The Caribbean.
How did they measure that?
You can tell by take a core from the bottom of the ocean.
Okay.
And then you look at what was living in the ocean.
Yeah. Okay.
And there are species that love really cold water, and there are species that love warm water, and they alternate.
Brilliant. That's great.
Well, this is still not. It's another one of those graphs, but still not the one I have in mind. But the other one was the first one would suffice.
Was it this one?
No. This was a horizontal graph, not a vertical.
Horizontal.
Oh well.
But yeah, the first one was
like
great.
this.
Yeah.
This is horizontal.
No, still not the graph I had in mind.
Too many.
Well,
graphs.
I don't know, Mike.
But the first one was
great.
was fine.
Yeah.
Yeah, I think it was
Because
even a more
it
simple
illustrates the
version
point.
of that first one.
It illustrates the point that we are at the high end
Yeah.
of
Yep.
the we're
And
at a
it's somewhat
peak, and
regular.
Yep.
the peak of this heartbeat. We're in the upswing, and we're due for a downturn.
Yep.
Yeah. So this is a short reading I'll do from a book by Gene M. Grove, published in 1988, which is considered sort of the definitive work on the Little Ice Age, and is quite frequently quoted. And like I said, it's probably Jean, but it's a man. It's a male author, climatic historian, who wrote this book, and it kind of sums up something really what I've been talking about, but probably a little more articulate here. In the last few centuries, glaciers have advanced in the mountains of Alpine Europe and Scandinavia, in the Northlands, and indeed in most other moist and cold parts of the world. In the decades between the late 16th and late 17th centuries, European glaciers swelled and their tongues advanced, destroying high farms and damaging mountain villages. Streams fed from glaciers flooded more frequently, sometimes catastrophically. In many areas, this kind of hazard was compounded by landslides and avalanches triggered by increased precipitation and the greater glacial activity associated with it. For several hundred years, climatic conditions in Europe had been kind. Now, this is what we've been talking about, the medieval warm period. There were few poor harvests, and famines were infrequent. The pack ice in the Arctic lay far to the north, and long sea voyages could be made in small craft then in use. Communications between Scandinavia, Iceland, and Greenland were easier than they were to be again until the 20th century. Icelanders made their first trip to Greenland about AD 982, and later they reached the Canadian Arctic and may even have penetrated the Northwest Passage. Grain was grown in Iceland and even in Greenland. The northern fisheries flourished, and in mainland Europe, vineyards were in production 500 kilometers north of their present limits. The beneficent times came to an end. Sea ice and stormier seas made the passages between Norway, Iceland, and Greenland more difficult after AD 1200. The last report of a voyage to Vinland was made in 1347. Life in Greenland became harder. The people were cut off from Iceland and eventually disappeared from history towards the end of the 15th century. Grain would no longer ripen in Iceland, first in the north and later in the south and east. As the northern winters became colder, fish migrations took different tracks, and life became tougher for fishermen as well as farmers. In mainland Europe, disastrous harvests were experienced in the latter part of the 13th and in the early 14th century, with famines in England in 1272, 1277, 1283, 1292, and 1311. The years between 1314 and 1319 saw harvests fail in nearly every part of Europe. Extremes of weather were greater, with severe winters and unusually hot or wet summers. In consequence, the boundaries of cultivation contracted. In these late medieval times and in succeeding centuries, the impact of climatic fluctuations was felt most painfully and persistently in highland areas. Cultivated areas suffered especially in the uplands of oceanic regions. So then, this is now from another work, also talking about, this is the climate of Europe, past, present, and future, by Hubert Lamb, who was considered one of the godfathers of modern, not Hubert Lamb, Herman Sloan. And here's what Herman has to say. He's considered one of the godfathers, the founding fathers of modern climatic science, right? So this was his work from 1984, The Climate of Europe, Past, Present, and Future. And this was what he says, and this needs to be borne in mind by anybody who's going to have an opinion about climate change, okay? This is what he says. Climate, even under its natural development alone, varies continually, each year, each decade, each century, each millennium, since long before any question of impact of human activity. It is important to gauge the magnitudes and timescales of these variations, since planning should not be based on expectations of return to some non-existent norm. And the magnitude and extent of any changes attributable to man's activities, or even whether any such effects are occurring on more than a local scale, cannot be determined without knowing the range and the likely timing of changes due to natural causes. Extension of the record to earlier times by systematic use of the numerous historical documentary reports of weather available in Europe, as well as various forms of fossil or proxy data, indicates that the last 1,000 years saw a particularly great swing of the prevailing temperature level of more or less global extent. And this was accompanied by other changes, for example, of the wind and rainfall regimes that are largely determined by the global temperature level and its distribution. There was a long period of more or less sustained higher temperatures in this part of the world between AD 900 and 1300 or later, followed by a period of regression and glacier growth until between about 1550 and 1850, when there was probably the greatest extent of mountain glaciers and sea ice in both hemispheres since the last major ice age. So, yeah, I think this stuff is important to provide a context. He goes on. I'm gonna couple more here. There is more evidence from the last millennium. From both oxygen isotope work and forest studies, it seems clear that New Zealand underwent a sequence of temperature changes broadly paralleling that in Europe. From the variations of the glaciers in Chile and elsewhere, including those near the equator in Africa and New Guinea, it seems clear that the colder regime of the Little Ice Age centuries was worldwide in extent. Now, a lot of the criticisms and dismissals of the medieval warm period and the Little Ice Age was that, they were only regional, and so therefore they are not comparable to what is going on now. So this has been the argument to get around addressing the implications of those kinds of natural changes that we saw, example, medieval warm period, Little Ice Age. Going on with the quote here, from a variety of evidence, it seems that the colder climate, particularly in the 17th and 18th century, was subject to a wider range of year-to-year variations than the present century. The variations with which we are most concerned for planning purposes must be those on timescales from a single season up to 100 to 200 years. But it is worth noting in connection with the century-to-century prospect that a recent survey indicates that each of the last 3 millennium has produced a period of colder climate and advancing glaciers in its middle centuries after a warmer period around the beginning of the millennium. The longer-term variations also are therefore of more than academic interest. So I will... So what do you make of that, Russ?
Well, it does seem like that's very important for anybody looking at modern climate change. Mm-hmm. But I'm trying to figure out where are we going with that in terms of outburst floods.
Because, again, the thing there is that the outburst floods are basically a phenomena that was exclusive to a particular epoch of time.
Okay.
Epoch of time that we're essentially have come out of.
Right.
There will still be outburst floods because there are still, lakes pooling up against glaciers, but not at the scale they were 50 years ago or 100 years ago.
Right.
So one of the things so let's dive into some of the idea of some of the research that's been done around modern glacial outburst floods. And what we're going to find, I think we've already gotten into that somewhat.
Yeah.
But I'm going to jump back to an early work by a glaciologist named J.W. Glenn, who wrote a paper in the Journal of Glaciology back in 1954. And in this paper and a couple of subsequent papers, he elaborated on what came to be called Glenn's Law. Okay, so I'm not going to get into the mathematics of it, but the narrative here will convey the idea. So this is from the abstract of the paper. It is well known that an empty hole in a glacier will fill in if it is more than some 15 to 20 meters deep, due to the rapid variation in strain rate with shear stress. In other words, as the shear stress increases, the strain rate, or the rate of deformation, you might want to think of it that way, will change in a glacier, right? So let's say you have a borehole. That borehole, because of the strain rate, will determine how quickly that borehole closes up, right? Now, crevices and fractures can form in glaciers, and then they can close again. So you can have a moulin, which is like a fracture that reaches all the way to bedrock, or you can have a crevice that can open up in a glacier, particularly because if it's a rapidly advancing glacier, there might be tensile forces that are actually pulling the glacier because it's moving down valley fast enough. Cracks open up, but those cracks, and called crevices, basically can close up again as well. So he's saying that it is well known that an empty hole in a glacier will fill in if it is more than some 15 to 20 meters deep due to the rapid variation of strain rate with shear stress. It is pointed out that a water-filled hole or lake will tend to enlarge itself by the same mechanism if it is more than 150 to 200 meters deep. Okay, so in other words, 200 meters will be exactly
like 600 feet,
656 feet.
Okay.
So this is what he worked out. The mathematics of it showed that once it reaches 200 meters in depth, or 656 feet, a water-filled hole or a lake, a body of water, will begin to enlarge itself by the same mechanism, because it'll cause actually movement of the ice itself. And then he says here,
so you're talking about a water-filled lake in ice. Is that what you're talking
yes,
about? Okay,
yes.
Okay. All right.
Yes. Or let's say that you've got a hole that's filled, and that hole is 600, 700 feet deep, and that hole is filled with water. Well, what it's saying then is that pressure of that water will be enough to begin to enlarge, cause the hole to begin to enlarge. That's basically what it's saying when it's talking about the strain rate, the shear stress and the strain rate. So the strain rate is the actual change in form and shape that's going to take place. So if there's nothing in a hole, the ice will eventually close that hole. But if there's water in that hole, if that hole, and he worked out the theoreticals of it, was up to 200 meters deep, then the water pressure is going to be enough to actually, that the water itself will enlarge the hole. And it says, he goes on to say, this phenomenon is believed to be responsible for the periodical and complete emptying of some glacier lakes, such as been reported for the Tulsaqua Lake in British Columbia, Grenelon, and Grimsvötn in Iceland. He says recent experiments on the mechanical properties of ice have shown that whenever ice is subjected to a shear stress greater than about 1 bar. Now, 1 bar is simply atmospheric pressure, which is about 14 and a half pounds per square inch at sea level, right? So 1 bar is 1 atmospheric pressure at sea level. Maybe a little bit, not exact, but it's close enough for a ballpark understanding of this. So once the shear stress is greater than about 1 bar, flow takes place at a rate, and he's talking about ice flow, takes place at a rate which increases rapidly with the stress. An example of this is the filling up of crevices and boreholes in glaciers. For when a vertical wall of ice is more than some 20 meters high, the ice at the surface of the wall near the bottom is subjected to a vertical compressive stress of about 2 bars in addition to atmospheric pressure. So now, add the 2 bars and, you've got atmospheric pressure times 3. And at that point, the ice will begin to move and deflect, to deform under the pressure. In certain parts of the world, there exist quite large lakes which are dammed by glaciers, and it is certain that during various stages of the Pleistocene epoch, many others have occurred. Some of these lakes, for example, the Tulsequah Lake in British Columbia, empty from time to time, releasing a vast quantity of water to their outflow streams, which often causes catastrophic flooding in the valley below. In the case of the Tulsequah Lake, this water is known to emerge from a tunnel in the glacier snout. And Kerr, another glaciologist, has reported that immediately after an outflow, the lake is completely empty, which implies something. In some of the early ideas, the outburst floods were believed to result from the water overtopping the glacier and perhaps cutting a channel within it that allowed the water level to drain off over the top of it. But if the whole ice dam is not removed by the water, then the lake is not going to completely empty. So, but when the lake completely empties, what that suggests is that it drains subglacially or N-glacially, E-N, with an E-N, like within the ice itself or beneath the ice. The usual theory of this phenomena, as Glenn goes on to say, is that the water builds up until its surface level reaches that of the glacier, when it spills over and the escaping water cuts a channel in the ice and thus gives a catastrophic emptying. It is difficult to see, however, why this should completely empty the lake, and it seems more likely that the level of the water rises until the pressure at the lowest point of the lake exceeds that corresponding ice pressure sufficiently for ice flow to occur. Although at first the water will tend to spread equally in all directions along the bed, the enlargement of the lake under the ice in the downhill direction creates an increased pressure there relative to the other points, and thus the lake will dig itself a tunnel under the glacier until it either links up with a subglacial stream already present or emerges at the snout. In either case, a catastrophic emptying will occur, and the lake will be left completely empty. After emptying, the channel, now air-filled, will quickly close up again to restart the cycle. The Tulsequah Lake has a depth of about 150 meters, so that this process is quite possible, while the appearance of the newly drained lake apparently points strongly to subglacial drainage. So that's the idea that I think the prevailing idea is that most of these outburst floods are the result of the water going under the glacier or between the glacier and the channel walls, which is kind of what we saw with the failure of the Teton Dam, but not so much overtopping. At least the overtopping is not going to drain it all the way to the bottom. That's the point. If the lake drains all the way to the bottom, and by the way, 150 meters, which is now times 3.28. Yeah, so now that's considered one of the deepest lakes in modern history of glacially dammed lakes, which is about 490 feet in depth. Okay, so at that point,
he's saying that the water pressure at the bottom of the lake, once it reaches a certain depth, will begin to actually dig into the ice.
It will dig. It'll dig a conduit for itself.
Yeah, and that actually deepens the lake and increases the pressure until up to a certain point until it manages to.
Well, what happens then is the pressure. He's saying that once it reaches that 2 to 3 bars of pressure,
the
ice will begin to flow.
Oh, okay.
So it will begin to change shape. So now the water pressure, the water can actually force its way through.
Okay.
Now, once it actually gets through, now it's flowing, right?
Yeah.
Now that flowing generates heat.
And erosive forces.
That will begin to rapidly enlarge the conduit walls,
allowing
more water. And now you have a whole positive feedback process going on. And then the lake drains catastrophically.
Right. And because it was the pressure at the base of the lake causing this to happen, the lake can drain completely out because it makes a drain hole basically at the deepest part of the lake.
You got that.
And then once the water's all gone, then the pressure thing reverses itself and the ice closes the hole. And then the process can start over. Okay.
Yes.
Wow. All right. You want to take a break real quick and we'll come back and keep going on this? Okay.
Yeah. We'll look at some cool images that to understand the internal architecture of glaciers.
All right.
And why they would not make such suitable material for major dams.
Okay. We'll be right back.
Right.
And welcome back, ladies and gentlemen. Second segment, the destruction of the ice dam hypothesis. I suppose we're going to get there. We might have to make another show out of it. Who knows? But before we get back into that stuff, obviously we want to mention cbdfromthegods.com. I think Randall has something else to share with us about CBD
Well, not particularly. I mean, before we get into the CBD oil of the gods discussion, I thought there was a package that came today. So I thought, if it's okay with you guys, we'll do this first. Then we'll talk about CBD. It says it says U.S. postage and fee pay. Let's see, USPS priority mail. And okay. Oh, well, look at here. If you can see this, what it says. It's from the gods. I got a package
from the
gods. Well, it's about damn time.
And way to plug the Postal Service, Randall.
Oh. Well, hey, I do my part, right?
Right.
All right. So I better see what's going on in this box. Right. Okay. From the gods.
Okay. Hopefully it's not Pandora's box.
You think?
Yeah, does it say from the gods to Pandora? Because you probably shouldn't open it.
No, it says from the gods, and then in parentheses, it says Pandora. So, is that? No, you guys are making fun now. This is serious business.
Into a gateway. I've got it on recording here.
I'm opening. Well, what could possibly be in here? We better adjust the camera a little bit here. Let's see what we've got. What is this? Oh, look here. Bubble wrap.
Interstellar jumpsuit.
Yeah. Oh, I think it's been subject to a force of about 44 G's on the way down from out there. Okay. More. Wait a minute. What's this? What's this? Better have a look.
Savvy.
Yeah, I recognized all those packages for sure.
Hey,
Sav.
All right. And let's see what we got here.
Goo from the gods.
Gummies! More gummies! I'm so happy. And now,
Christmas at Randall's.
Not one, but two. Check it out. There I am. I was in one of, that was a few decades ago. I will admit I was a little slimmer then. My hair wasn't quite as gray, but hey, so I am good to go for another month.
There you go.
I am, man. Yes, sir. Well, I was getting down, and now my life is complete again. I feel secure. I feel warm and fuzzy. And because I know that I've got all my goodies, I've got muscle rubs ahead of me. Yeah.
Where's your microphone?
Good sleeping nights.
I'm
good to go, man. All right. Thanks, guys. Thanks, gods. Appreciate it. Cool.
All right. Pick that camera back up.
Oh.
There we go. That's better. But before we get into that, cbdfromthegods.com. Use the
go there for all your CBD needs.
There you go. Yeah.
Help us out.
Yeah.
Yeah, man. And you'll do yourself a favor too. I'm convinced now.
Coming soon, hair regrowth salve.
Well, I've been suggesting that to Mike Robertson here now for months, that they need to start, including a brand of salve that you can rub on your head and.
Oh, they could
just
definitely
don't rub it on your back.
Yeah.
Yeah.
Make sure it doesn't get under your back. Yeah.
You don't want that. No. Yeah. You ever see these guys with the hair coming up out of their shirt? And yeah, that's what I'm afraid of.
It'll keep you warm in the next ice age.
Yeah, it is.
So.
That's
the definition of warm and fuzzy.
That's what I was getting to. That's the whole point, is when it gets colder, people generally grow more hair.
Yeah.
It's a physiological response to the changing climate.
Yeah.
Okay.
Brad's doing well in the Holocene.
Yeah. Yeah. Okay, so here's a study that was done. This study was done in 1958 by J.B. Sissons in Geographica Annular, which is a Dutch paper, a Dutch geographic paper that's been around for a long time. They do publish a lot of interesting stuff on glaciers and
like a journal. Is that what you're talking about?
Yes, it's a journal. This was from volume 40, published in 1958. And it's referring to a paper that was published in 1902. I'm not going to go back to that. But this 1902 paper was probably one of the first published observations of this whole process that we've been talking about. Whereas the glaciers are shrinking back, they form ice-dammed lakes. The author of this paper was Kendall, so it says that since the publication of Kendall's well-known paper in 1902, it has been widely accepted that the withdrawal of glacier ice from higher to lower ground caused small ice-dammed lakes to be formed in valleys in many parts of upland Britain. These lakes overflowing from one to another across spur crests, resulting in the formation of channels that are now streamless or contain misfit streams. Now, his use of the term misfit streams, what do you think that he's referring to there when he says misfit?
Underfit rivers.
Underfit, yeah. So here he is in 1958. He's observing that a lot of these glacier meltwater streams in Britain seem to be underfit in terms of the creeks or rivers flowing in them. He says it will be suggested that the sites of many postulated ice-dammed lakes were probably largely occupied by glacier ice at the times the lakes are supposed to have existed. Now, he's talking about Pleistocene ice here, right? 12, 13, 14,000 years ago. And that the channels on the spurs between, now, do you know what we're talking about when we say the spurs? Picture, you've got like two hills with a valley between them. And the hills come out and they're foothills, let's say. and there's a tributary valley between them and a main valley in front of them. So those hills come out and they're truncated at the main valley. They're referred to in that configuration as spurs. Okay, spurs.
All right.
It will be suggested that the sites of many postulated ice-dammed lakes were probably largely occupied by glacier ice at the time the lakes are supposed to have existed, and that the channels on the spurs between, because the hollows in between have the glaciers in them, right? And the spurs between are usually not overflow channels from these lakes, but were cut by streams supplied mainly by water held within or flowing through, beneath, or over the ice that occupied the valleys between the spurs. So, in other words, he's looking at these features and he's moving away from a gradualistic scenario to one now that is trying to come up with an explanation for what he's calling the misfit streams. And he's saying rather than there being a whole series of small proglacial lakes, one after another, cascading in effect, one forming, melting, leading into another, it forming, melting, and this taking place over long periods of time, what he's saying is that he's looking, and the evidence seems to be that there's water within the glacier or flowing through the glacier or beneath the glacier or even over the ice that occupied the valleys between the spurs. Now, I would suggest that we might be even consider that all three things were happening at once. That we have subglacial waters flowing beneath the glacier. We have N-glacial, remember that term, Englacial, N-glacial within the glacier, or supraglacial on top of the glacier. I think we can see that evidence at the Flathead Lobe up in western Montana, that you had water flowing over the top of the glacier, and that is what cut Chief Cliff, and we'll be showing Chief Cliff in an upcoming, probably within the next couple of episodes, because we're going to get into looking at the basin of the lake. After we've kind of gone through and looked in more detail at the ideas behind and the what we now know about outburst floods, we're going to circle back and then relook at some of the evidence within the Missoula flood Channeled Scablands region. So he's saying that they were cut by streams supplied mainly by water held within N-glacial, flowing through, also N-glacial, beneath, subglacial, and or over the ice. So he says and/over. So he's actually thinking that perhaps more, it's not just limited to one mechanism, that you may have water flowing over the glacier. Now, water flowing over the glacier, and I would suggest that the same mechanism holds true, say, for the Okanagan Lobe, which you guys have seen. Now, here picture water flowing over the glacier is going to discharge at the snout of the glacier there at the Withrow Moraine. You're going to have subglacial floods coming out and channelizing and forming the head of Moses Coulee, and possibly even water flowing through the glacier itself. So he goes on to say that the first part of this paper is concerned with demonstrating how the suggested interpretation applies to a selected area, namely the Edelston Valley, which is in Scotland, and its immediate vicinity, which is about 12 to 19 miles south of Edinburgh. The relief of much of this area was ideal for the development of ice-dammed lakes, draining from one to another across spur crests, but the numerous meltwater channels and the abundant deposits of sand and gravel show that no such simple pattern developed. Instead, this evidence shows that large volumes of meltwater flowed through and beneath the ice, as well as along its margins. In the second part of the paper, certain major difficulties encountered by the orthodox ice-dammed lake hypothesis will be considered, and it will be suggested that the author's interpretation of the Edelston Valley evidence and that of other areas may be applicable to considerable areas of Britain. and I might say to Europe as a whole. See, so back there in 1958, here's a guy now who's basically been brought up to think totally in gradualistic terms, but he's looking at this and he's wanting to go there. I mean, he's admitting, look, here's these underfit, these huge valleys and channels with little streams flowing in there. And he's looking at this model that they're saying there's, this succession of small ice-dammed lakes, one leading into another. And he's saying, well, wait a second, that is not consistent with the vast volumes of sediment that we're seeing. It's not. And so then he goes into the paper to talk about the difficulties of some of these more gradualistic ice dam models. Okay, so Annals of the Association of American Geographers, 1963, Kirk H. Stone, who was a specialist on the Alaskan ice-dammed lakes. So in south central and southeastern Alaska is one of the world's major concentrations of lakes dammed by glacial ice. There are 53 of these lakes in an area about 800 miles long and 100 miles wide. However, until 1951, only the presence of some of these lakes was recorded in print, and a small number of them were known locally for irregular or periodic disappearance. It is likely that the occurrence of an ice-dammed lake is a result of a combination of several regional characteristics, in addition to local conditions of topography, supply of moisture and ice, weather, and climate. All of these require analysis. In general, it appears that the larger lakes have about the same characteristics of site as the smaller, but most of the larger lakes are known to empty and refill, either regularly or irregularly. So there's a cycle, and the cycle might be something like this. The lake fills up enough, the pressure on the heel of the ice dam gets great enough, the water can now force its way into the ice, under the ice. Eventually, it will force its way all the way through. Now, we know from Vatnajökull under the Iceland ice sheet, when that eruption goes off, you have a reservoir of water that is roughly 30 miles from the discharge point at the south rim of the ice sheet. Typically, 1 to 3 weeks, it's gonna have managed to go work its way through 30 miles of glacial ice, and then discharge. So, of course, what happens is it starts with a trickle, and then that trickle rapidly turns into a flood peak, and then it'll start as a trickle, it'll go to a rapid flood peak, and then it'll taper off because as the pressure is dropping, the force driving the water forward and through the ice is also diminishing, right? Proportionately, as the water falls, the pressure is diminishing. Now, at some point, depending on how much of that ice is left, while the water is forcing its way under, it can cause decoupling between the bottom of the ice sheet and the substrate, whatever that might be, whether it's bedrock or glacial till or whatever. Boom, it separates. Water is flowing under, and that pressure is keeping the ice mass buoyant. Water levels dropping, pressure is diminishing, and at some point, if that ice volume has not been removed by the force of the flood, it'll settle back down, and it can reseal the bottom. And then, and if it does that before the water's completely drained, then there'll be some residual water left. But in most cases, it appears that that's what happens after the water has fully drained, because the water flowing through there is also generating heat, which melts the ice back as fast as it can settle down. Once the water has flowed through, now there's no pressure keeping the ice buoyant. It settles down, reseals the valley, and now the lake starts refilling. Once it reaches the critical threshold, the same thing happens again. So he goes on to talk about the 16 larger of these lakes. 11 of them are known to empty regularly or irregularly. This is possibly a distinguishing characteristic because signs of emptying were observed at only 5 of the smaller lakes. Because the smaller lakes have not yet attained the requisite pressures to overcome the resistance of the ice. The actual process of emptying is only partly known. It has been observed in detail at only Lake George and Tulsaquah Lake, and in general at a few other Alaskan ice-dammed lakes during aerial observation or by the interpretation of air photos. In a preliminary report based on fieldwork in 1951, all such drainage was noted to be under the damming ice, most often by undercutting along the rock-ice contact for all of the distance to the end of the damming glacier, but at no place by overflowing the damming ice. Previous limited observations concurred, and additional evidence strengthens the conclusion that most of the world's ice-dammed lakes probably empty through sub- or end-glacial channels. And ice is known to be honeycombed with channels. So, in talking about the mechanics of emptying, probably there is more than one way. At Lake George, it was observed to be by subglacial movement of water along the rock-ice contact. At Tulsaquah, it is interpreted to be by lifting of the damming glacier's ice until old or new openings under or in the glacier are found. At only a few lakes are the data on depths available, but it is probable that at many, the water is much below 9/10 the height of the barrier. Now, at 9/10 of the barrier, what happens? Well,
The ice becomes buoyant.
Ice becomes buoyant, exactly. Further, it is known that the depths at the beginning of the Lake George outlet, now get this, was 114 feet in 1951, and at the lowest part of Tulsaquah was 73 meters. And interpreted depths at other lakes are much less than a proposed requirement of 150 to 200 meters. Now, what he just said is extremely important, because what Glenn did was formulated, the first glaciologist we discussed there, he was the one who formulated the theoretical limit of 150 to 200 meters depth, which we calculated was, 650 some feet. Well, now, in what Kirk is describing here, he says again, he says, it is known that the depths at the beginning of the Lake George outlet, which is 114 feet, right? And at the lowest part of Tulsaquah Lake, which was 73 meters, 73 is, we'll say, is 240 feet, basically. And interpreted depths of other lakes, they are much less than the proposed requirement of 150 to 200 meters. So in other words, that 150 to 200 meters is the theoretical limit. But in the real world, it's almost invariably quite a bit less than that before the ice fails. And we saw some of that in the last episode, that, we looked at a couple of specific examples of lakes and showed that in terms of their volume, in terms of their peak discharge, they're minuscule relative to the flows from Lake Missoula and the flows that created the Channeled Scablands. Study of the emptying of these and other ice-dammed lakes in the world has disclosed the probability of multiple mechanisms for emptying, which are dependent upon combinations of at least hydrostatic pressure, density, and orientation of crevice patterns, slope characteristics of the beds of the lake. In other words, the steeper the slope, the more your G, the acceleration due to gravity, is going to be within your equation, right? So, obviously the steeper the slope, the greater the pressure, right? Hydrostatic pressure, density, orientation of crevice patterns, slope characteristics of the beds of the lake and the damming ice, water temperatures, weather and climate, stability of the damming glacier, and reflection or radiation of solar or earth heat. 9 of the Alaskan ice-dammed lakes are known to have emptied more than once. 5 of them are larger lakes, which once emptied annually, and 3 still do. Now, this is very typical, annual emptying of the lake, because every year you're going to have spring melt. It's going to feed the lake's going to grow, and then in late summer when it reaches its maximum, boom, the ice dam fails, the lake drains, and so you have a so-called self-dumping lake. But, it shows over and over again that the ability of ice to constrain volumes of water at any given pressures is certainly constrained by the nature of the ice itself. Now, here's from Austin Post and Lawrence R. Mayo, 1971, glacier-dammed lakes and outburst floods in Alaska from the Hydrological Investigations Atlas HA-455, published by the Department of the Interior, United States Geological Survey. Glaciers in Alaska cover about 73,800 square kilometers, which is about 28,500 square miles. They are most highly concentrated along the Pacific coast and in the south central part of the state. Many of these glaciers, as elsewhere in the world, flow across the mouths of adjoining valleys and can cause lakes to form behind the ice streams. These glacier ice dams are subject to repeated failure. It should be noted that large quantities of water can also be stored in or under glaciers and may create serious floods even though no surface lake is visible. Such catastrophic floods have occurred in Iceland so frequently that the Icelandic term jökulhlaup is now used internationally to describe them. So again, this is the idea that the larger the lake, the more readily it's going to fail, right? The larger lakes typically tend to fail oftentimes every year. They don't continue to accumulate water for 50 years or 100 years until that water is 2,000 feet deep against the damming ice.
But going back to the beginning of the earlier points, is this like this process of jökulhlaups or these outburst floods? Is this all a process of the gradual recession of the glaciers? Like, in other words, when they're growing, are you getting these big outburst floods annually?
No, it's more so a phenomena associated with the shrinkage of the glaciers.
Okay, so
because as the glaciers they're shrinking through melting. See,
yeah.
So this is another important point.
Yes,
is that the lakes form as the glaciers are receding. When the glaciers are growing, yeah, you have meltwater discharging. Of course you do, but you don't have the occurrence of these huge glacier lakes like in the tributary valleys forming. Because remember the model: trunk glacier, valley glaciers. Valley glaciers start melting, right? Because they tend to be smaller. They might be more exposed to the sun, right? Down in the lower part of the valley, they might be in the shadows of the mountains, whatever. So you've got the tributary glaciers coming in from the side. They melt first, and they now form pools of water ponded against the main glacier. But that main glacier is shrinking and receding. So as it does, it allows for the discharge of those volumes of ponded water. And then what happens is when the cycle repeats itself, the next subsequent filling is typically going to be less than the preceding, because the amount of glaciers to melt and provide the water is diminishing, and the glaciers that can hold in the water as dams is also shrinking.
So based on these observations, someone would be wrong to theorize that an ice dam grew to hold back a whole bunch of water, and then it burst, and then the ice dam grew back and held back a bunch of water, and it burst.
I would say that that's a conundrum, because what we're assuming there is a situation where the lake is growing in volume at the same time the ice mass is increasing, right? So which is it? I mean, how do you have both at the same time? That to me is a rather sticky proposition. Because for one thing, if the ice, see, here's the thing. You've got two types of glacier ice, temperate glacier and polar ice. And then you got subpolar, but that's kind of in the middle. But on one extreme, you've got a polar glacier, which is frozen to the substrate. Well, that's an environment where there's no seasonal melting. It's cold all year round for a polar glacier that's completely frozen to the substrate. And it's not moving very fast because it is frozen to the bedrock or the ground anyway, right? Now, a temperate glacier is different because it's subject to seasonal melting. It's in a temperate climate. And so it can actually, the snout of that glacier will melt back in the spring and summer, and it'll grow in the winter. But depending, again, on how much snow is falling over the accumulation zone. But so we saw from the Little Ice Age is that the lakes, as the glaciers shrunk, the lakes increased in size. Right? And up to a point. And then the lakes began to diminish in size. Right? Because initially the glaciers are big, they're swollen. Right? They're bigger than they've been in 10,000 years. Now they start melting back. So that's when these lakes start forming 150 to 200 years ago. Now what happens is that they're seen to periodically dump. And sometimes that dumping can be regular, sometimes it can be irregular. In the case of some of these Alaskan lakes, they were seen to dump every year. So every year, the water would force its way through the dam, wouldn't destroy the dam completely. But in the Missoula flood scenarios, you got to destroy that dam completely. You're not going to be discharging 9.6 cubic miles of water from the Clark Fork River Valley and not completely wash away the entirety of the ice dam blocking the mouth of the river.
Okay,
right?
that's what I was going to say, because I was starting to see like, okay, they're saying these things can break and not that they go under the glacier or they work their way through it, but they don't totally wash it away.
No, they don't.
Right. But in this case, with the Missoula one, there's so much water, and the evidence of the flows downstream from that, there's so much water that it would basically have had to tear away all the ice to get that kind of flow.
Yeah.
Yeah.
So I showed a couple of graphs last episode. Strone Lake. Let's see. It began to drain when the depth reached 125 feet. 125 feet, right?
Let me ask a question in here, Randall, because
sure.
it seems like it's got to be a factor. Because during the depth of the ice age, or even as it's waning, right, the global temperature is average 15 or 20 degrees less for the whole planet, or at least probably the hemisphere. I mean, that's winters are colder, summers are colder. The ice has to be thicker, denser, harder, whatever. I mean, it seems like it's tough to compare the outbreaks and the things that are happening today versus that when the whole planet is in that 20 degree lower temperature all the time.
Well, 15 degree, but that's, it's the same point. Yeah, I mean, yeah, it's tricky to work out, but you still have the situation of, 600 cubic miles of water filling those valleys and an ice dam blocking the mouth of one of those valleys. And then it has to extend another minimum of 30 miles unless the steepness of the ice, the margin of the lobe is unrealistically steep. Typical marginal profile would suggest in order to be a half a mile thick over Lake Pend Oreille, it has to extend at least down to Spokane, right? Not just to the south end of Pend Oreille where it's frequently depicted. Because, you're talking about from the south end of Lake Pend Oreille to Clark Fork, you've suddenly gotten a half mile of ice. That's not typically what we see. We typically see this, not this. So, so this particular, the volume of this lake, which drained completely, it reached 125 feet. It drained completely. It was 0.003 cubic miles. So if I divide 0.003, that means that the volume of Lake Missoula was 200,000 times more than this particular example. Estimated average discharge, 2,500 to 5,000 cubic feet per second. Estimated peak discharge, 15,000 cubic feet per second. So we could go there and, what did I say, 15,000? So peak discharges of some of the Missoula floods, like through Rathdrum Prairie, was only 53,000 times greater. Now wrap your head around that and get why I'm skeptical when you say, well, we can just look at modern ice dam events and extrapolate up from that. And that's essentially what they're doing.
Yeah.
To go on here, then there's Lower Salmon Glacier and Summit Lake. The average depth at failure of this particular Summit Lake was 140 feet. So divide by 140. So that means that Lake Missoula at its ice dam was 15 times deeper than Summit Lake, which would be one of the deeper lakes at 140 feet. Volume of the lake, 0.04. So miles, so 0.04. So this was a little bit bigger. So Lake Missoula was a mere 15,000 times larger than this lake. And the estimated peak discharge of this lake, 40,000 cubic feet per second. So that's one of the bigger, the letter Q in the equations is used to represent discharge. Capital Q means peak discharge. So capital Q in this case, 40,000 cubic feet per second. So we will do at 40,000 cubic feet per second. Peak discharge of Lake Missoula, only 20,000 times bigger. Now, you see why I'm skeptical of the whole ice dam theory. Are you beginning to see? So, we could go on. I have study after study after study. Here's an ice-dammed lake in Norway, a big one. Annual studies over a period of 12 years have demonstrated, the lake drained on at least 10 occasions in the last 12 years. Right? So it goes on. I mean, we could talk about, this ice-dammed lake. Average depth, the volume of this lake was 12 million cubic feet, which I haven't converted to cubic miles yet. But same thing. I mean, we could go the average. Okay, so the estimated peak discharge. This was a big catastrophic outburst flood in Norway. This was published back in 1988 in the Journal of Glaciology. Okay, here we go. The volume of the lake, Lake Missoula volume was 12,000 times bigger than this lake. And peak discharge, 1,278 cubic feet per second. So that means that the peak Missoula flood peak discharge was a mere 626,000 times greater. So, I mean, we could go on example after example after example. Now, after we've done this, if we've looked at 10, I mean, how many of these modern lakes do we have to look at before we say, okay, we're looking at something very different here, and that we may not be so secure in our assumption that we can just extrapolate up orders of magnitude and say, oh, well, self-dumping modern lake, we'll just expand that idea to encompass Lake Missoula. And we looked at Russell Fjord last episode, but I've got some interesting photos here we'll wrap it up with. There's so much more we could get into. Here's another. Yeah, I mean, I have dozens of examples here. We barely scratched the surface.
Right, but what it comes down to really, right, is the problem of ice being the damming material.
Yes.
That's really what we're getting down to, because you can't extrapolate up orders of magnitude if the ice material begins to fail long before that, right? No matter what.
At 3 bar.
Yeah.
Yeah.
I mean, that's what did you say the pressure, the PSI would be at 1,000 feet depth in water?
At 1,000 feet, well, it's going to be half. I mean,
450.
pressure at the heel of the ice dam at 2,100 feet is somewhere in that neighborhood of 950 to 960 psi.
Yeah. So 3 bar is like,
Yeah,
or 2 bar. What was it? 3 bar or 2 bar? Because that's only like 40.
3
something.
bar, 3 bar. So, yeah, there's a
42
lot of
PSI.
really interesting literature on this. And of course, in what I'm writing, I'm getting into much more greater depth on that. But what we'll do here is I'm going to just share screen so you can actually see some of the architecture of glaciers, which further shows evidence of why they would probably not be capable of impounding water to any considerable depths or pressures.
Oh, God. Well, this is definitely an experiment we could do, right? We can build an experiment and put a piece of ice as like some sealing a container with water and then pressurize the container up to 42 PSI and see if it purges its way through the ice, right?
Yep.
What's the breaking point?
We could definitely
Presumably, if I understood what you're talking about,
We'll figure it out.
we'll figure it out. Okay. I was thinking it might be easier just to like detonate a hydrogen bomb down in this hole and see what happens.
You're right. That might be easier.
So, but yeah, so this is the kind of thing. Let's go through some of these here. You got deep holes and fractures and crevices in glaciers, in addition to an interstitial conduit network. So you've got holes, you've got tunnels. Now imagine even you're trying to do a dam of concrete, solid concrete. Well, and then you decided, well, hey, let's put a bunch of caves in that dam. I think this has got to be, I'd get with Darren and let's see if we can't do some glacier field trips.
Yeah.
Let's do our next contact at the cabin up on the Greenland ice sheet.
Yeah. Jump down in one of those holes and see how long it takes you to come out the snout of the glacier.
Yeah. Okay.
Contact
In
with the cap.
In a barrel.
Whoa.
Yeah, check this out. So, I mean, this is what you're dealing with glaciers, particularly temperate glaciers, because temperate glaciers, you've got the water that, percolates in and through, on top of, under, and that moving water generates heat, and that heat creates openings and holes and caverns and caves and tunnels. So I think it's fair to question how this medium could be more proficient at retaining water at pressures 3 times that of modern engineered concrete, steel reinforced, bedrock grouted dams. I think that's a fair question to ask. Look at this.
Yeah, I love that photo.
Yeah.
Me too.
Awesome.
And this one.
Yeah, no, we could definitely do that.
I would think so.
Yeah.
And
Yeah,
then
until it opens the hole to the snout while you're in there.
Or that closes.
Yeah, it closes.
or it closes. That's the thing that would concern me even more. Yeah, all of a sudden the walls start moving in.
Exactly.
Oh,
And you just turn that kayak sideways and try
Yeah.
to swim out real fast.
Block it.
Block-
but I think you get my point here. Subglacial stream emerging from the snout.
Yeah, look at that. Wow.
Yeah. So I definitely think we've got some glacier field trips we've got to plan at some point.
Yeah.
I mean, we can start with the Columbian ice fields up in British Columbia if Canada ever decides to let normal people in again. Or maybe,
What about Glacier? What about Glacier National Park? Is that still is that a good place to go to look at that kind of stuff?
Yeah, the glaciers have shrunk quite a bit.
Yeah.
Can you actually get up to the glaciers in Glacier National Park?
Well, I think so.
they had the big exhibit that said all these will be gone by 2020.
Yeah,
and they had to take that exhibit down.
Those signs
still
down.
there.
They are still there.
Oh, I remember that.
Yeah, they're
I'm
still
trying to
there.
extrapolate that up to, excuse me, Mike, to Moses Coulee, and Jameson Lake that we were up against into,
exactly
coming out the snout of that Withrow moraine.
Yeah,
exactly. Except this might be 10,000 cubic feet per second, if that, coming out of here. And we're looking at 300 million cubic feet coming out the snout. Although I would conjecture that you also had superglacial flows coming on top. I would conjecture that Grand Coulee was partially cut anyway by a superglacial flow being focused along the interlobate zone between the Okanagan lobe and the Columbian lobe. I think I pointed that out on a map in the previous episode.
Yeah.
If not, we'll be coming back to that.
And those flows would be a lot more destructive to the glacier than a subglacial flow, obviously, because once the subglacial flow channelizes, it can even, preserve the glacier, like this one here.
Mm-hmm.
That water's flowing in the ground. It's eroded some of the glacier, like you said. The glacier might be pushing down on the top of the flow a little bit.
Mm-hmm.
But if it was superglacial or inglacial, it would just be ripping the glacier apart, right?
Yeah.
Eroding it.
One, you would assume that the water too it's supra, SUPRA,
Yeah.
super glacial. Okay,
what I
it's
said.
coming over the glacier. I thought you said super glacial.
No,
that's not allowed. That's like
that's a band name. Super glacier.
Super glacial.
super glacial. Okay, yeah. I have the same kind of reaction to that as when I hear somebody talking about something supposedly is this or that, and they say, well, supposedly. And I want to take them aside and tell them that there's no letter B in the word supposedly. So anyhow, that's a topic for another podcast.
Right. Well, supposedly a super glacial flow would be heavily erosive.
Yeah, supposedly it would be very erosive. Yes, because for one thing, flowing over the glacier, right? It's if it comes to a deep crevice or a moulin, at least some of that water is headed straight to the bottom of the glacier.
Yeah.
And this is where all of this kind of information, I think, is going to help lead insight if we start envisioning what happens with a hypervelocity impact into an ice sheet.
Yeah, that's the thing. We had talked about that. You had brought up the supraglacial flow idea a couple episodes back, and I, in the context of an impact, it seems hard to believe that you would have that for any great distance, because it would be so fractured that it would eventually just exploit the cracks and find its way down to the bottom.
Well, it does that, but bear in mind that for hours and hours after the event, if not for days, you're going to have intense precipitation right back out onto the ice sheet. If the impact, maybe beyond the ice sheet. And I think that, you would have huge sheets of meltwater, some of which is going to immediately find access to the base.
Right.
And I think there with a hypervelocity impact into an ice sheet, right there, you've got the mechanism for introducing huge volumes of subglacial water under high pressure virtually instantaneously and bypassing the need for a reservoir of water, either on top of the glacier, either a superglacial reservoir or a subglacial or inglacial, whatever that reservoir of water is. And before John Shaw's passing, that's, as we've discussed, that was kind of what he was tentatively proposing, because without something like, a hypervelocity impact, or perhaps maybe a solar flare, or some external means of triggering a huge energy dump able to melt huge volumes of ice, you think, well, without that, you go naturally, you've got to form some kind of a reservoir. And that the drumlins are formed by these huge reservoirs of water that suddenly breach some threshold, and now they're able to form sheet floods under the ice sheet. But a hypervelocity impact, you've bypassed any need for a reservoir because you've got an instantaneous melting. You've got a mechanism that will simultaneously melt huge amounts of ice and also give that meltwater access to the base of the ice sheet. So my question is that if it turns out, and I've suggested that the direction that our thinking should go, that if we start looking at what the lessons of these modern outburst floods teach us, is that there are limits, there are thresholds beyond which they don't go. And, Glenn's law, is basically shows that once the water pressure against the ice reaches certain levels, the ice begins to deform. In other words, the water can overcome the ice, you see, or even just under atmospheric pressure, the ice will flow. So now we didn't even get into the studies showing the interstitial or the network of veins within the ice itself that could serve as conduits. And then they could eventually merge, and then you have this capture process where several of these conduits, small, even micro scale conduits, but there's still water moving through them. They merge, but each time they merge, the amount of heat against the enclosing conduit walls increases. And so it slowly increases at first. And then as it increases, it captures more and more of the smaller conduits. And then eventually it reaches a threshold. And now the conduit begins to enlarge catastrophically, and the water, boom, gushes out. Because in some of the cases, it was seen that there were trickles preceding the major outburst flood. So that's the idea. If we look at it, the ice dam theory becomes untenable, then we have to look at some other mechanism for producing that meltwater. And there's a lot more we could get into, but I think we probably reached the end of the road for tonight.
Yep. I think your dog just came in to say hi.
Oh, hello, dog. I think you're right.
Yep.
Well, I've trained the dog now to come in and
notify
let me know when it's time to wrap it up.
Podcast is over.
Yeah, podcast is over. Which dog is it? For those that don't know, Johanna James has posted over the last weekend or a few days ago a synopsis that she did. Listen to all 10 hours of our Cosmographia Atlantis podcasts and kind of did a Cliff Notes version. 22 minutes, I think. And she does a pretty admirable job of giving a fair and accurate summary. Of course, she doesn't get into the depth that we could in 10 hours, but I'm impressed nonetheless. Yeah. I just wanted to mention that and give a shout out to her.
Shout out.
I think she did a good job. And
yep, we'll include a link to that. Yeah, always check the video description for links on things like that. And also our social media, because we got a bunch of events coming up. Also our Lower Cumberland tour in the backyard there out in Alabama and Tennessee. Good stuff there first week of November. So yeah, definitely sign up for the newsletter at randallcarlson.com/newsletter, and you'll get all the updates on this stuff. And watch our social media. We got a manager there, Laura, that's running a bunch of cool stuff, and she's making the graphics, and you get reminded of those events if you're keeping up with us there on most of them are the Randall Carlson. Twitter is Randall W. Carlson.
W being the initial of my middle name, in case you were wondering. So yes, and I'll also mention that Yeah, any sales or presentation of my work over at Sacred Geometry is unauthorized, and I'm not there anymore for multiple reasons. And just want to let people know that you purchase anything or subscribe to that site or anything, not one penny of anything sales of my work at that site comes to me. It all goes to the administrator of the site. So
Yeah. So
RandallCarlson.com.
RandallCarlson.com is the place. And the Sacred Geometry classes that are being sold there are a 10-year-old unfinished beta version. So please be patient because there's going to be an upgrade coming soon this fall. So don't spend your money there. Wait for the real thing coming from the source.
Yeah. All right, guys.
Yeah, it was great.
Show. Yeah.
Great show. Enjoyed it.
Yep.
As always.
Stuff.
See you guys
Thank
next
you.
week. Thank you.
Next week. Good night, guys.
Good night.
More.